So now I'm going to do question 1. We're going to do the multiple choice questions. Just going to start from 1.1, which says that inertia is a property of an object whereby the object, option A says that the object needs a force to accelerate. Option B says that the object comes to rest when the force that has set its motion is removed. Option C says that the kinetic energy, it has a kinetic energy, the object. D says that is not able to move. So we all know what inertia is, right? It's a property that resists motion. So the option here is D, which says that inertia is a property of an object where the object is not able to move. Now we're going to go to 1.2, which says that a box of mass m rests on the floor of a surface which is accelerating upwards. The lift acceleration is A, and the acceleration due to gravity is G, right? The net force of the box is equal to what? So we're having a lift and we're having a box like this, right? And we know that the force of gravity is acting here and the applied force is acting up, right? So to find the net force, F net is equals to the force minus the force of gravity, right? So the force being m multiplied by acceleration minus mg, right? So this would be our net force. So our answer here will simply be C, right? Because we have our force here with acceleration and then subtracting the force with our gravitational acceleration. So this would be the answer C. Then 1.3 says that a learner drops an object from the 15th floor of a high building. 1 second later, the learner drops another identical object from the same position. As both objects are free fall, the distance between them is, so you're dropping, so this is the floor of the building, right? Let's say it's 20 meters and you're dropping, so you're dropping it, you're not throwing it, you're not you're just dropping it. So it's gonna go down, so this ball is gonna go down. Ball A will go down, right? And ball B will also go down after 1 second, right? So the distance between these, because it's a free fall, gravity is acting upon this ball, pulling it downwards, right? And the same with B, right? So the distance between them is going to increase. Obviously, if maybe you consider air resistance, which will try to prevent it from going down, trying to keep it up. So the distance between ball A and ball B will definitely increase, right? So we're just gonna take option A, which says increase. Now we go to 1.4, which says that a trolley with a mass m is moving at a constant velocity v on a frictionless track. A block of mass m is dropped on the trolley from the above. The final velocity of the trolley will be, so now you're having a situation where F is equals to ma, right? And the initial, so this is the initial force, right, of the trolley. So which means if it's traveling at constant speed, which means acceleration will be 0, right? So it's going to be 0 newtons, the force, right? So now what happens is we're having both mass of the trolley and the mass of the block that is thrown inside the trolley, and then we have our acceleration here. So to find the velocity, let's say F is equals to, so now because we're having the mass of the trolley and the mass of the block, these mass are both identical, so it's just 2m and acceleration, and we know acceleration is equals to v, change in v over t, right? So you can simply say equals to 2m change in v over change in t, right? And to find the the velocity, you simply want to say cross multiply. You have F multiplied by change in T is equals to 2 M change in V, right? And then you divide by 2M, divide by 2M. So your change in V is going to be equals to 1 over 2 multiplied by F delta T over M, right? So you can see that our change in velocity, our velocity final is going to be half, right? So the final velocity, because the initial one was 0, right? So the final velocity will be half. So you can simply take option C as the answer. Then now we are doing 1.5, where an AC electric motor has power rating of 1.2 kilowatts. In 1 minute, the amount of work done by the motor in joules is. So what you can do here is this. So what you can do here is this. You can to find the work done by this power, you say power is equals to work done over change in T, right? And then you cross multiply, you have work done is equals to power multiplied by change in T. So the power that we have is 1.2 kilowatts, so you can multiply by 10 to the power 3 the kilo. And then time, you can simply use seconds or minutes. Let's just use the minutes, so it's 1 minute, right? So the work done here is 1,200 watts, which you can also write as joules, right? So you can say work done is equals to 1,200 joules. So this is the answer that I'm getting here. It's actually this option A here. I know in the memo you will find this answer here. So if by any chance your calculations you find this answer, please let me know in the comment section below. But otherwise, this is what I'm finding, option A for this question here. So now we're going to do 1.6. 1.6 says that a car travels at constant velocity. So the car travels at constant velocity towards a stationary listener. The car's hooter emits a sound of constant frequency as it approaches the listener. Which of the following statements regarding the frequency and the wavelength of the hooter are observed by the listener? So the first option says that both frequency and wavelength have decreased. So if, let's say, this is the listener, right, and this is the car, and the car is coming in this direction. So as the car comes in this direction, the wavelength decreases, right? The wavelength decreases. It decreases. So we know that V is equals to F times lambda, right? And we're observing frequency and wavelength, right? So if the wavelength decreases, right, then what happens to the frequency? So frequency is equals to V over lambda. So if wavelength decreases, then the frequency becomes higher, right? So it increases. So they're inversely proportional. So if we look here, because this car is coming towards the listener, so it means now that the wavelength is decreasing. So where in the option wavelength is decreasing? So this is the option for wavelength is decreasing. This is another option for wavelength is decreasing. So between these two options, they're right. This one is wrong because the wavelength is not increasing. This one is wrong because the wavelength is not increasing, right? So looking at these two options that I just underlined here, let's look at the frequency now. As the wavelength decreases, the frequency increases. So where is the frequency increasing? It is increasing on only this option here. So which means this option A goes out, out, out. We will consider option D in this case to be correct. right? Because the frequency increases as the car comes closer, whilst the wavelength decreases. Okay, so now we're going to 1.7, which states that the number of excess electrons which will cause a charge of -8 microcoulomb sphere is equals to. So we need to find the number of electrons, right? So the formula is N is equals to the charge over the charge of electrons, right? In this case, we have minus. You can put the minus if you want, or you don't have to. I'm just going to write 8 times 10 to the power of -6 because it's macro, divide by the charge of an electron, right? Which is 1.6 times 10 to the power of -19, right? So the answer, you just punch this in the calculator and see what you find, but you'll definitely find this answer here, which is 5 times 10 to the power of 13. Right, so these are the number of excess electrons, 5 times 10 to the power of 13. So the right answer here is B. Okay, so now we move to 1.8, which says that 4 identical light bulbs are connected, as you can see. So we have 1 light bulb, 2, 3, and 4 light bulbs, right? Then they say, how does the brightness and potential difference of L4 compare with the brightness and potential difference of L1? So what you need to note is this. If we're comparing L4 and L1, right? L4 is in parallel with L3, right? So these are parallel. So the fact that they are parallel, it means now if you write your V is equals to IR, which means now that the current is distributed equally, right? So it's distributed. If maybe we have a current of 2 amperes, sorry, then it means now that 1 ampere is going to go to this one, 1 ampere is going to go to this one. So current is distributed in each, right? So for the fact that this one would have 1 ampere of current, it means now that the voltage will be smaller. The voltage potential difference of this one will be small compared to the potential difference of L1. L1 potential difference would be larger, right? Would be larger compared to L4, right? And then if the potential difference is smaller, definitely the current of L4 will be smaller also, right? The current, which is I, will be smaller because I said if we are talking of 2 amperes and this L1 has 2 ampere and these only share 1 ampere because they're identical, remember that. So it's going to be 1 ampere, so current is smaller. So this just tells you that L4 will bright less compared to L1. So we can take this answer here, less. And the potential difference of L4 will be less compared to L1, right? So we'll take this option here, as I indicated that the potential difference of L4 is going to be smaller due to the current, right? And then the potential difference of L1 will be larger. So the right option here is A. Then we go to 1.9, which says that which of the following devices cannot operate with both direct current and alternate currents, right? AC and DC, right? Currents. So one obvious answer here is just going to be B, right? These other ones can operate in both currents, so the transformer will not. Fine. Then we go to 1.10, which says that in an experiment on the photoelectric effect, a scientist shines a green light, right, on a metal surface, right, and observes electrons ejected from the metal surface. So later the sensor shines a blue light. So this is important. So it first shines a green light, then shines a blue light. So these two lights have different wavelengths, just so you know, with the same intensity so the intensity is the same, but we don't know the wavelength of these two properties of light, right? So which of the following statements will be correct, will be the correct observation? So the first statement says that the number of ejected electrons per second increase, the number of electrons increase, the number of ejected electrons per second will decrease, the maximum kinetic energy of the ejected electrons will increase, the speed of ejected electrons will decrease. So how we can analyze this, we need to know your visible light spectrum and know the wavelengths of your, okay, you don't really have to memorize them, but you need to know that if this is the blue light, right, and it goes up to the red light, so you need to note that the wavelength, what is the wavelength? Does the wavelength increase or decrease, and going in which direction? So the wavelength going in that direction, it increases, right? Increases. So you need to know what other properties of light come after. So there's blue, and then here in between you can find your green light, right? And then going up to the red light, right? So you know that going in that direction, your wavelength increases, right? So if your wavelength increases, what happens? Fine. So because I'm more interested in analyzing the kinetic energy here. Why? Because your E energy, photoelectric energy, is equals to your H multiplied by C over your lambda, which is equals to the work and kinetic energy, right? So we want to note whether which kinetic energy will increase, right? Whether it will increase or not, because we first use the green light, and the green light is this one here, which is here. So basically, the green light has because wavelength increases going in that direction, which means green light has a higher wavelength, right? Compared to the blue light. The blue light has small wavelength, right? And we are starting from the green light to the blue light. That's how we are lighting in this experiment. So it means now that if you go to this formula that I just indicated here, it's going to be H multiplied by C over, because we're starting from the green light, so the green light, right? And then I transpose this W to the other side. We have minus W is equals to kinetic energy, right? So the kinetic energy of the green light is going to be smaller, right? Why is it smaller? Because it has a higher wavelength, right? The wavelength, it's here, wavelength is higher compared to the blue one. And since we're starting from green to blue, then it will change. It's going to be, instead of being the green light, now we'll change and use the blue light, right? So the blue light has a small wavelength, right? So the fact that the wavelength is small, which means the kinetic energy will be larger. So the kinetic energy is increasing from the green light to the blue light, right? So we can simply take option C now in this case, because now we know that kinetic energy increases from a property of light that has higher wavelength to a property of light that has lower or smaller wavelength. So now we're going to do question 2, which reads as follows. An empty lift is supported by a steel cable. The lift moves upwards at a constant velocity, while an upward force of 2,500 newtons is applied by the cable. Ignore the mass of the cable and all frictional forces. Now, 2.1.1, we are asked to state Newton's second law of motion. So Newton's second law of motion states that so if you have an object like this, right, and you have a force acting on this object, this force will cause the object to accelerate in the direction of the force. So the force is going to the right. If this, let's say this direction is to the right, so which means this object will accelerate in the direction of this force here, right, causing, because the force is equals to ma. So once the object moves in the direction of the force, it will result in acceleration being directly proportional to the force, but acceleration being inversely proportional to the mass of the object, right? So let me state it. When a resultant force acts on an object, the object will accelerate in the direction of the force, right? So so now causing acceleration to be directly proportional to the force and inversely proportional to the mass of the object. So that is your Newton 2. Question 2.2 says that draw a free body diagram indicating all forces acting on the lift while it travels upwards at constant speed. 2.2, we having this lift object. I'm gonna indicate it using this dot here. So this is our lift and forces acting on it. The first force is the force of gravity that is acting on the lift, and the applied force which comes from the tension that causes the lift to move vertically upwards, right? So which was given as 2,500 newtons, right? So you don't need to write it, but you can simply say force, right? So yeah, this is the free body diagram of the lift. So 2.3, write down the magnitude of acceleration of the lift as it moves upwards. So remember, they said acceleration, they didn't say gravitational acceleration. So the object is moving in the direction which is up, right? So meaning there's only one acceleration that is acting on this body. It is the gravitational acceleration, which has the force of gravity being F of g, right? So this means now that the acceleration of the object, because it's moving vertically upwards, then our acceleration is going to be 0 meters per second squared. 2.4, calculate the mass of the empty lift. So now we want to know the mass of the empty lift. We must make sure that we take into account the information that was given in the statement. We have the applied force of 2,500 newtons, right? And what we know is that it's traveling at constant speed. So the lift is traveling at constant speed, right? And what we also know is that the free body diagram of the lift is the force applied and the force of gravity below. So we're just going to write our F net. So F net is equals to MA, right? So the net force is the force applied minus the force of gravity, right? So that is our net force of this problem here. So it's going to be force applied minus force of gravity is equals to MA. Remember that we were told that the lift is traveling at constant speed. So what that means is, you know, speed is equals to displacement over time, right? But acceleration is equals to speed over time. So if this speed is constant, then it basically means that the final velocity minus the initial velocity will give you 0, right? Divided by time. So acceleration will definitely be equals to 0 in this case. So meaning you have f of a minus f of g is equals to m, because we want the mass, but we know acceleration is equals to 0, right? So we have f of a minus f of g is equals to 0, and the force applied is 2,500 newtons minus, so f of g is equals to mg is equals to 0, and we have 2,500 minus the mass we don't know, but we know that g is 9.8, and then we equate to 0. Then we can transpose this portion to the other side. So we have 2,500 newtons is equals to 9.8, and then m we divide it by 9.8, we divide by 9.8, and our mass in this case is going to be 255.10 kg. Now we're going to do 2.5, right? When the 2,500 force on the cable is replaced by a force of 3,000 newtons, the lift accelerates upwards. Calculate the magnitude of this acceleration. So now that we have increased the force that is applied, the lift starts to accelerate, right? So now we want to know the acceleration of this lift. So what we need to take into account also in this problem is the free body diagram of the lift, which we know the force acting on is the force applied, which in this case our force applied is going to be 3,000 Newton, and we know that it's F of g, which is the gravitational acceleration, or the gravitational force, sorry. So we are going to write our F net. So it's going to be F net is equals to ma. We are looking for the acceleration, right? So our F net is going to be the force applied, because the object is moving vertically upwards. So the force applied is going to be positive. We're going to take upwards as positive, minus the force of gravity is equals to ma, right? Remember that the mass is calculated as 255.10 kilograms from the previous question. So the force applied is 3,000 newtons minus our m, which is, so it's going to be mg is equals to ma, right? And 3,000 newtons minus our mass is 255.10 multiplied by 9.8 is equals to 255.10. Let me remove this, and then it's going to multiply with the acceleration. We're just gonna divide this whole thing with 255.10 divided by 255.10, and then our acceleration is going to be equals to 3000 minus 255.10 times 9.8 divided by 255.10. So please punch this into the calculator. You should get your acceleration being equals to 1.96 meters per second squared. Now we're going to do 2.6, which says that identify the force that forms a Newton 3 force pair with the weight of the empty lift. So if we draw the lift, it looks like this, right? And if we just consider this flow of the lift, if you just enter a lift, if this is you entering the lift, you know, okay, you're gonna enter here, and this would be the flow. So this is the flow of the lift, and yes. So now there'll be a force of gravity acting on this lift, and then because there's tension ropes that are attached to this lift, moving it vertically upwards or downwards. And so let's just consider the tension to be here. Let's say there'll be a force here, right, causing upward movements instead of me considering this tension. So this is actually the force that causes Newton 3, right? Because the lift's weight, or the gravitational force of the lift, wants it to move downwards, but the force wants it to move upwards. So you can simply write the force of the empty lift on Earth. So that would be your answer for this question. Now we're gonna do question 3, and the above statement reads as follows. A boy standing on a bridge projects a ball, which is ball A, vertically upwards with an initial velocity of 5 meters per second. The height of the bridge is 20 meters. Ignore air resistance. So 3.1 says that give the magnitude and direction of the acceleration of ball A as it leaves the boy's hand, right? So we're having this ball and it's projected vertically upwards, right? Obviously the motion is going to move like this. So now the only force that is acting on this ball as it moves upwards is the gravitational force, right? So meaning that our acceleration for this question is going to be 9.8 meters per second squared. Now going to 3.2, it says that calculate the total time it will take for ball A to reach the road. So what we have here is this scenario where we have this bridge. Let's say the bridge is connected from this point A to point B, and then this person here is going to throw ball A vertically upwards, and it'll go down like this. So this is the height, which I'm gonna indicate it's y1, and then just below the bridge is the road. So this would be the road, and this is the final point of ball A. So what we are most interested in is the time it took for the ball to reach ball A, right? T of A. So for us to do that, we know the initial velocity is equal to 5 meters per second, and the final velocity here at the top is equals to 0 meters per second, and we know that the velocity at this point is also v equals to, let me just say velocity and not say initial because it can change. So let me say v is equals to 5 meters per second, right? And now what we know is that the height from this point up until this point is 20 meters, right? We were told that the height is 20 meters. So now we are going to find the time of ball A at the road, right? So for us to find this, we first need to identify the time it will take the ball to reach this maximum height, right? So if the time it will take for the ball to reach this point here, and then after that we'll go straight to the bottom of the road, or the road rather, right? So just going to indicate with the diagram. So the initial is from this point going to the top part, right? So I'm just going to find the time it took for the ball to reach the height, the maximum height. T is equals to, so we know the v initial is equals to 5 meters per second, and the v final is equals to 0 meters per second. So we're going to use the equation v final is equals to v initial plus g multiplied by t, where the v final is 0 but the v initial is 5, plus our gravity is going downwards, so we will take down as negative, so it's going to be minus 9.8 multiplied by t, right? We want to transpose the 5 to the other side. We have minus 5 is equals to minus 9.8 t. Then you divide by minus 9.8 both sides, and our t is going to be 0.510 seconds. So this is the time that it will take the ball to reach that maximum height. So t is going to be 0.510 seconds, right? So now we are going to identify the time it will take the ball from this maximum height all the way up to the road, right? So how we can find that is, let me do this. So just gonna read through the diagram. So it's from the maximum height where v initial is equal to 0 meters per second. If I consider it as v initial, and at this point it's the v where it's equal to 5 meters per second, so it's still at the top of the bridge, and then there is our y1, and then we go straight to the bottom where there's the road. So now we're interested in the time it will take from the maximum height all the way to the road. T is equals to, so what we will do is this: we are going to first find the height, because we already know excuse me, we already know the height or from this point. We know the height from this point is given as 20 meters, right? We were told that it is 20 meters, and but we don't know this y, right? So we can find that y, where we can say v initial is equals to 0 meters per second, v final is equals to 5 meters per second. So by finding this y, I want us to use the total height all the way from the top to the bottom to find time, right? I'm just going to indicate it as y3. So let's first find this y1 here. So it's going to be v final is equals to v initial squared both sides plus 2 multiplied by g multiplied by change in y. So the v final is going to be 5 squared is equals to v initial is 0 plus 2 multiply by your 9.8 and then change in y, right? So if you divide, because you're going to have 5 squared is equals to 2 times 9.8 times change in y, and then you divide both sides by 2 times 9.8 divided by 2 times 9.8. So your change in y is going to give you 1.276 meters. So that is your y1. y1 is equals to 1.276 meters, right? So now that we found our y1, so meaning that the total height from the top where our velocity is 0 all the way to the road would be the total height is equals to y1 plus 20 meters, which is 1.276 plus 20 meters, giving us 21.276 meters. So that is our total height, right? So we'll use the total height to find time. So you can simply say y is equals to v initial multiplied by t plus 1 over 2 multiplied by g t squared. Our initial velocity, remember that our initial velocity is 0 meters per second. If we are saying we're starting from this top point, right? The reason why we're starting from this top point is because we are using maximum height and we're going all the way down, right? So our initial velocity is 0 meters per second. So making this portion here being equals to 0, right? So we're gonna have y is equals to 1 over 2 gt squared, right? So because we have our y, our maximum height, which is 21.276, so we're gonna write it 21.276 equals to 1 over 2 multiplied by 9.8 meters per second. So you're just going to write t squared there, and then you're going to cross multiply. So you're just going to cross multiply here. It's going to be 21.276 multiplied by 2 divided by 9.8 is equals to t squared. So you're going to put the square root both sides, and then your t is going to be equals to 2.0837 seconds. So this is going to be your time from the maximum height all the way to the road. So hence we're going to write it here, which is going to be 2.0837 seconds, right? So now, because our ball moved from the starting point going all the way up to the point of maximum, going all the way down and straight down to the road. If this is the road and if this is the bridge, the time, just going to indicate the time. The initial time that we found here is equals to 0.510. Now, and then the time it took from this point of maximum all the way down to this point, it's t is equals to 2.0837 seconds, right? Now we're just going to add these two times because this is the initial point, right? So you need to calculate the time from the initial point all the way down to the road, right? So we're going to add this time here and this time here to get the total time. T total is equals to 0.510 plus 2.0837. Then we're going to get 2.59 seconds. So now the statement says that at the same time that ball A is thrown upwards from the top of the bridge, another ball B is projected up from the road. Ball B has an initial velocity of 14 meters per second. 3.3 says that we should calculate how far apart ball A and ball B after 1.2 seconds. So what's going to happen is this. This ball A is going to move like this, and we don't know which point it's going to reach, but what we know is it's going to reach maximum height here, and then it will go down. But if you remember clearly that the time it took for it to reach maximum height from this point here on the bridge was equals to 0.51 seconds. This is from the previous question, right? So that neglecting air resistance, we can assume that the same amount of time will be experienced, t being equals to 0.51 seconds, right, from this point up to this point, right, where here the velocity is also 5 meters per second, right? So now the whole point is of me doing this and this is to just give you the time, the total time. 0.51 plus 0.51 is equals to 1.02 seconds, right? So this means now that it took the ball 1.02 seconds to reach this point here, right, of the bridge. So the reason why I'm showing you is that we are told to calculate how far ball A and B are between each other after 1.2 seconds. So this tells me that 1.2 seconds will be after this point. It will be here, probably somewhere here. Ball A will probably reach, just to write it nicely, 1.2 seconds might be somewhere here. So if it continues to move, and maybe let's say this is the point, let's assume 1.2 seconds will be this point, because from this point it's actually t being equals to 1.02 seconds, right? So here let's assume t is equals to 1.2 seconds, right, for ball A, right? So now what's going to happen is this, ball B, which is this one here, will move. Let's say this is ball B. It moves vertically upwards. Let's say it reaches this point, and this point is where t is equals to 1.2 seconds, right? So what you are seeing here is ball A and ball B facing each other as they are projected, right? So we are more interested in this height here, the difference in the height between ball A and ball B, right? So for us to be able to calculate that height, we will use the total height, and then we'll subtract it with this height here, because we should calculate this height, let's say y of A, and we'll calculate this height here, which is y of B, and then we subtract both heights from the 20, which is the height of the bridge, and then we'll be able to get this height here, which, let me just indicate height between A and B, right? So the whole point now is to calculate this height of A, and secondly calculate the height of B, and then we'll continue the rest. So for us to do that is let me just write here ball A, right? So for me to calculate the y of A, we're going to use the equation of y is equals to v initial multiplied by t plus 1 over 2 gt squared, right? For y of A, right, this one here. So to find this y of A, we know that our initial velocity is 5 meters per second if we consider from this point of the bridge, right? So it's going to be equals to 5 and then the time it takes for it to reach this point is equals to 1.2, right? It's going to write 1.2 there, and then plus 1/2 into the gravity is going downwards, right? So it's just going to be negative. So this will be negative 9.8, and time is 1.2 squared. And the y that you're going to get if you punch your calculator is going to be so you're gonna get minus 1.056 meters. So the minus just tells you that the object is moving downwards, right? So this is just the direction of the height of this ball, right? So we now found y of a, right? So we already found y of a, this one here, which is equals to minus 1.056 meters. So now we want to find y of b, right? So to find y of b, we're gonna say ball b, y of b. So we're going to use the same equation. So it's y is equals to v initial multiplied by t plus 1/2 gt squared. And we'll substitute the initial velocity, which is this one here, 14 meters per second. And then the time is 1.2 plus 1/2 multiplied by g. We know g is going downwards, so it's 9.8, and 1.2 there squared. So the y that you are supposed to get for this y of b is equals to 9.74 meters. So it means now that it will reach 9.74 meters. So we're just going to write it next to it, so it's equals to 9.74 meters. So now that we found y of a and y of b, we can easily find y of AB, which y of AB stands for the difference in height between the two balls, right? So for us to find that, we will say y of AB, which is the difference, is going to be 20 meters, which is the total height of the bridge, minus y of a minus y of b equals to, so it's 20 meters minus our y of a is going to be 1.056. I know we wrote it as negative here, but once you substitute it here, you substitute it as positive because the negative stands for the direction of the height. And then we're gonna minus the y of b, which is equals to 9.74. So if you subtract minus 1.056 minus 9.74 from 20, you're gonna get y of AB being equals to 9.2 meters. So this is the height that ball A and B are apart from each other. So that means now this this point here, y of, so this means now that this y of AB is actually 9.2 meters. So now the tennis ball A hits the road below, stays in contact with the road for 0.2 seconds before it bounces up at a velocity of 14 meters per second. So in 3.4, we are asked to draw a velocity versus time graph for the motion of ball A from the time it was projected up from the bridge until the time it rebounds to a maximum height. Clearly indicate the following on your graph: the initial velocity of the ball, the time when the ball hits the road and it is in contact with the road, the velocity of the ball when it rebounds from the road. So remember the motion of the ball A. If we say this is the bridge and this is the road, then ball A's motion started from this point going upwards all the way to this point going downwards up to this point. So what we are told is that it became in contact with this road, the surface of this road, and then it bounced upwards, right? So we don't know up to what height, but we know that it bounced. So when it started bouncing and going up, the velocity started being equals to 14 meters per second, right? So we're most interested in finding out the final velocity, right? So I just want us to find the final velocity after it was in contact with the surface, right? So what we're going to do is this. We're going to say we're going to take the time. So we know that it was in contact with the surface for 0.2 seconds, right? And another thing is the initial velocity. The v initial here was equals to 5, meaning here it is also v equals to 5 meters per second, right? And we know the height of the bridge being equals to 20 meters, right? So the first thing we can find now is the final velocity as it reached the ground. What is the final velocity, right? As it moved from the initial velocity of 5 meters per second going downwards. So what you want to do is going to say v final squared is equals to v initial squared plus 2 multiplied by g multiplied by change in y. So we want the v final, so the initial is 5, so it's going to be 5 squared plus 2 into g, it's minus 9.8, and our change in y, if we just consider the height from this point going to this point, because the initial velocity is 5, right? So we're just going to start at that point. So we're just going to say 20, which is negative because of the direction. And then you can just square everything up because we want v final squared, right? So it's going to square everything up and we're going to find v final being equals to 20.42 meters per second. So this is the final velocity as the ball reached the floor of the road, right? Or the surface of the road rather. So v final is equals to 20.42 meters per second. So now that we found the final velocity, then what we can do now is want to find out the velocity of the ball as after it bounced off the surface, right? Because what happens is, as if we consider this as the surface of the road and the ball bounces, when it bounced, its initial velocity was equal to 20.42, right? Because it was coming from the top and then it bounced, and then immediately after bouncing, the velocity here initial is equals to 14 meters per second, right? So we want to find the velocity here, v final velocity, right? The reason why I want us to find the v final is because of this last statement in 3.4.3 where it says we must indicate the velocity of the ball when it rebounds from the road, right? So what we're gonna do here is this. We're gonna say because we found this v final here being equals to 20, right? So we're gonna say v final is equals to v initial plus gt, right? So the V initial, we're going to consider this being V initial, so it's going to be 20.42, exactly as I wrote here, plus our gravity being equals to minus 9.8, and the time is the 0.2 that it's spent with the surface, so it's the contact time. And the velocity that you're going to find here, it's 18.46 meters per second. So this is the final velocity of the ball, right? So if we draw the velocity versus time graph of this situation here, is gonna look like this. So this would be our Cartesian plane, looking like that, and then this, from this point here, this is our initial velocity where it was 5 meters per second. So V for velocity, T for time. So the object started at initial velocity of 5 meters per second. It went up until it reached maximum height, which was 0 meters per second. Then it went down, reaching the same velocity of 5 meters per second. Then it went down, further down, up to the final velocity, which I calculated, V final being equals to 20.42 meters per second, which is this one that I calculated. So this would be your first line of sketch. So these are the points, and then it became in contact with the surface, right? So the contact time was 0.2. So let me just indicate here. So this is the contact time, 0.2 seconds with the surface of the road. Then it started moving. So now the velocity of this object here, we're just gonna consider it as 18.46 is the velocity. Then it moved upwards up until it will reach maximum height where the final velocity will be 0. So this would be our second sketch of this problem here. So yeah, this would be your velocity versus time graph. Question 4. The statement reads as follows. A car with a mass of 900 kilograms is moving east and collides with a freestanding barrier that has a mass of 3,200 kilograms. Study the following momentum versus time graph of the car and barrier below and answer the questions that follow. So what we have here is a diagram that shows the collision between the car and the barrier. So this is the starting point. Just going to indicate the starting point here, where this would be the car. Initially, it had a momentum of 18,000 kg meters per second, and the initial momentum of the barrier, it was 0, right? This is the one. So the barrier had a momentum of 0 because it was standing. It was just still and not moving. So the car hit the barrier, and then the barrier started to move. Hence, you see the momentum is going up in this diagram, and the car's momentum started to decrease slightly, going to a negative momentum of minus 144, right? So now let's answer the following questions. In 4.1, we are asked to state the law of conservative the law of conservation of linear momentum in words. So the answer to this question is the law states that the total linear momentum of an isolated system is conserved. So that is the law of conservation of linear momentum. Now let's go to question 4.2. It says that use the information given in the graph and calculate the following. So 4.2.1, we are asked to find the speed and direction of the car. So the speed and direction of the car. How are we going to find the speed and direction of the car? We know very well that this is the initial momentum of the car, and this is the final momentum of the car, right? And the statement wants us to find the final velocity and the direction of the car, right? So which means we're going to focus on this momentum here. We're going to focus on this momentum here, which is minus 144. And so the equation that we're going to use is P is equals to mv. So that is the equation of momentum. The momentum is minus 144 is equals to, so the mass of the car, let's go up. The mass of the car is equals to 900 kilograms, right? So we're just going to write that 900 kilograms. So it's 900 kilograms and then multiplied by V. Then we're going to divide by 900 both sides, 900. So the velocity of the car is equals to minus 144 over 900, and the answer that you need to get is minus 0.16 meters per second. So that is the velocity of the car. The final velocity of the car is V is equals to minus 0.16 meters per second. So which you can simply write as 0.16 meters per second. So the negative specifies the direction. Remember that the car was moving east, and because of that, we consider east to be positive, right? So the negative means that it's no longer going in that east direction, so it's going opposite of east, which is west. Hence, we're going to just say the final velocity is equal to 0.16 meters per second, and then we specify the direction, which is west. So this is the answer for 4.2.1. So now in 4.2.2, we are asked to find the impulse on the car, right? So to find the impulse of the car, we're still going to use the diagram, right? So we have our initial momentum and we have our final momentum of the car, right? So for us to find impulse, we know the equation for impulse is change in momentum is equals to force multiplied by change in t. So the change in t is formed by the final momentum minus initial momentum is equals to F multiplied by change in t. So the final momentum, as I stated, it's this one here. So it's minus 144. So it's minus 144 minus into the initial momentum. It's this one here, which is 18,000, and then equals to F times delta T, right? So it's going to be minus 144 minus 18,000 is equals to F times delta T, right? And then we're just going to add these two here. So we're going to have F delta T is equals to minus 18444 Newton per second, right? Newton second, sorry. And the direction, because we are having a negative sign, and we said east is positive, so meaning it's going in the west direction. So that is the direction of this impulse here. So now what we're going to do is we're going to do 4.3, where it says, is the collision elastic or inelastic? So for an elastic collision, the initial kinetic energy must be equals to the final kinetic energy. So therefore the system is inelastic and is elastic, sorry. So for an inelastic system, the initial kinetic energy must not be equals to the final kinetic energy. So we need to prove by using the kinetic energy formula. Fine. So now what we're going to do is we're just going to write the initial kinetic energy, which is equals to 1 over 2 mv squared initial of the car plus 1 over 2 mv squared of the barrier, right? So what's going to happen here is the initial velocity of the barrier was 0, right? Because the barrier was just standing there, it was still. So the v initial of the barrier is 0, making this whole expression equals to 0. And then we will have the initial kinetic energy being equals to 1 over 2. So for the car, the mass of the car is 900. And we need the velocity of the car, right? So for us to find that velocity of the car, we know very well that the momentum. So for us to find the initial velocity, we know the momentum initial, which is equals to 18000. We know the mass, which is equals to 900. So it's easy for us to find v, right? So meaning we're just going to say P is equals to M over, So this means we're going to say P is equals to MV. Because we want V, we're just going to divide by M both sides. So V is equals to P over M. And then momentum is equals to 18, so it's going to be 1800 divided by the mass, which is 900, right? So this would be your velocity, which would give you 20 meters per second, right? So this is the initial velocity of the car. So now the velocity of the car is equal to 20. So when I substitute it here and put squared, and the answer that you need to get is 180000 joules, right? And then now we want the final kinetic energy, EK final, which is equals to 1 over 2 mv squared final plus 1 over 2 mv squared final. So I'm going to start with the car, so it's going to be 1 over 2, the mass of the car is 900. The velocity of the car we calculated in the previous question 4.2.1 of the final velocity of the car, and we found to be 0.16 meters per second. So you're going to square it, and then then you add plus 1 over 2, the mass of the barrier is going to be 3000. It's 3200, right? So the mass is 3200, and the velocity of the barrier, we know very well that there is a barrier there, so its momentum is this one, so P is equals to M times V, and then V is equals to P over M, which P is 18144 divided by the mass, which we were given to be 3200, so it's going to be 3200, and then the velocity would be equals to 5.67 meters per second. So we're just going to substitute that velocity here, so it's going to be 5.67 squared, and the answer that I'm getting for this here is 51 449.76, right? So the EK initial is equals to 18,000, and then the EK final is going to be equals to 51,449.6, right? So the initial kinetic energy is not the same as the final kinetic energy, so therefore we can conclude and say EK initial is not equals to EK final. So this now means now that the system is inelastic collision. Please pardon me with the background noise. It's beyond my control. Now we're gonna do question 5, which we have a 2-kilogram trolley which is at rest on a horizontal frictionless surface, and a constant horizontal force of 8 Newton is then applied to the trolley over a distance of 3 meters. So this is the trolley that we're talking about. It has a force of 8 newtons and it is applied across the 3-meter distance, right? So at point A in the diagram above, the force is removed. So at this point here, the force is removed. The trolley moves a distance of 7 meters up the incline until it reaches the maximum height at point B at this point here. So the trolley experienced a constant frictional force of 1.5 newtons while moving up the incline. So remember that between this point here and this point, the surface is frictionless, right? And then from A up to B, there's a friction of 1.5 newtons. Cool. So now we're going to do 5.1, which says that define a non-conservative force. So a non-conservative force, it is a force that which the work done in moving an object between 2 points. So it is a force for which the work done is in a moving object between 2 points. So if you have these 2 points here, and then there's a force that causes work done between these 2 points from this start point up until A. So that is a non-conservative force. And 5.2, so we're done with 5.1. Now 5.2 says that draw a free body diagram indicating all forces acting on the trolley. So this trolley here, as it moves along the horizontal. So I'm just going to draw on the trolley the free body diagram. So it's going to look like this. So the trolley is just stationary, right? And it has a force of gravity, and then it has a normal force, and then it has force applied like this. So the free body diagram will look like this, right? Cool. Now we're just gonna do 5.3, which says that state the work energy theorem. So the work energy theorem states that the net work done on an object is equal to the change in kinetic energy. So this basically explains the equation which says that the work done is equals to the change in kinetic energy. So that is the work energy theorem. Okay, so now we're going to do 5.4. So 5.4 state, okay, sorry, 5.4, this one here, which says that use energy principles to calculate the following. So we have 5.4.1 says that we must calculate the speed of the trolley when it reaches point A. So we want the speed of the trolley when it reaches point A, when it reaches this point here. We want the speed of the trolley. So we need to know forces that are acting on the trolley, right? For us to be able to calculate the speed of the trolley. The first thing that we're going to do here, we know that there's a force applied of equals to 8 newtons, right? That is acting horizontal. And we know that there's a distance of 3 meters, right? And yes, so that's what's important at this point, and that there's no friction. So we can simply use the equation of the work done, right? Where work is equals to change in kinetic energy, right? We know that the initial kinetic energy initial is equals to 0. Why? Because the trolley is stationary, right? So we're just simply gonna have the final kinetic energy, the EK final, right? You're gonna have that. So you're gonna have work being equals to the change in kinetic energy. So the whole point here is to find the velocity, right? So we know that work is equals to the force multiplied by horizontal distance and the angle. Cos of theta is equals to the change in kinetic energy, right? So we know the force, we know the distance that is acting, and then cos of theta. So the object is moving at 0 degrees, right? You know your Cartesian plane, so depending on where your 0 is, if your 0 is here and your 90 is here and your 180 being here, 270. So remember that the Cartesian plane of physics and maths are different. So if the object is moving in that direction, so it's the angle is 0, right? But if there was friction that it was acting, then the angle was going to be 180, right? So the object is moving in that direction, so the angle is 0. So now we know the angle, we know this, and we know this. And I told you that here the initial kinetic energy is equal to 0. So we're just going to use the formula for the final kinetic energy to calculate further. So now just by writing this here, so I'm just going to write F multiplied by delta X cos of theta is equals to change in kinetic energy, and the force is equals to 8, and then multiplied by distance of 3. Cos of 0 degrees is equals to the final kinetic energy, which is 1 over 2 mv squared final minus initial, which is 0, right? So what you're going to do is we're just going to substitute the mass of the trolley, which is 2 kilograms, right? So let me see if I can write here nicely. So we're having the force multiplied by distance, right? Cos of theta being equals to the change in kinetic energy, right? And the force, as I said, it's 8 newtons. Distance is 3. Cos of 0 degrees being equals to half mv squared final minus half mv squared initial, right? So this is minus, this is half. So this is equals to 0. So we're going to have 8, 3 cos of 0 degrees equals to 1 over 2 the mass of the trolley is 2, we want V final, and this 2 will go away with this 2, so you're going to have 8 multiplied by 3 cos of 0 degrees being equals to V final squared. So just going to square both sides, and our V final, not squares like this, so it's just going to be V final being equals to 4.90 meters per second. So this is our final velocity of the trolley at point A. Now we're going to do 5.4.2, right, which says we must calculate the height that the trolley, the height h that the trolley reach at point B, right? So what we know is that this trolley from A to B, it's going to experience friction, right, of 1.5 newtons, right? So at this distance. So what we need to note is that because we want to find the height, we know that this is h, right? But the initial height at point A is 0. So we know that, but the final height is what we want to find out. And we can also involve the equation of kinetic energy, right? And we can simply say that the initial velocity at A will definitely be involve the velocity of 4.9 meters per second that we just calculated in the previous question. But we know that the V final here at this point is going to be 0, right? Because it's just going to stop at point A, right? So we know that the final kinetic energy is just going to be 0. So if you want to write your work done, you can just say work done is equals to the change in potential energy plus the change in kinetic energy, right? And your work done on your left hand side, you can simply involve friction because it's the only force that is acting on this object in the incline, right? So you're just going to say the force, which is the friction, and then you multiply it with the distance that is acting on it, and cos of theta being equals to change in P of E plus change in kinetic energy. So this is the equation that you're going to use to calculate the height at this point here. So what you're going to do now, we're just going to rewrite the formula. So it's going to be work being equals to change in potential energy plus change in kinetic energy. So we have the force, frictional force, multiplied by the distance that is acting on it, cos of theta, being equals to the kinetic energy, the final one. So it's mgh final minus mgh initial. So just going to put brackets there and plus the kinetic energy. So it's going to be 1 over 2 mv squared final minus 1 over 2 mv squared initial, right? So the frictional force, as I said, it's 1.5, so it's just going to substitute 1.5, and the distance that is acting on it is 7 meters, right? The horizontal distance, yes, it's at an incline of cos of 180 degrees, right? Which is equals to, as I said, the final height is definitely going to be included. So let me just rewrite it properly. So we're going to have mgh final, but the initial one is 0. So this is just going to be 0 because at point A, there's literally the object is at a horizontal surface. And then the final velocity, as I said, is going to be 0 because that's where the object is going to stop. So you're just going to involve minus 1 over 2 mv squared initial, right, at point A. So you're just going to substitute, so it's going to be 1.5 multiplied by 7 cos of 180 degrees is equals to the mass of the trolley, which is 2, 9.8, and the height that we are looking for, minus 1 over 2, the mass is 2, the velocity, the initial velocity at point A, which is what we calculated in the previous question of 5.4.1, was 4.90, right? So it's going to be squared, and then we're just going to transpose this to the other side. So it's just going to be 1.5 multiplied by 7 cos of 180 degrees plus, so just gonna cancel out this first before I transpose. So you're just gonna have plus 4.90 squared being equals to 2 multiplied by 9.8 h of f, right? So we're just gonna divide with 2 multiplied by 9.8. So see that I didn't write my answer as yet because I wanna round off poorly. So I'm just gonna write this. It's just gonna be cos of 180 degrees plus 4.90 squared divide by 2 times 9.8, right? So now you can just punch this entire answer. So let me just remove this to not disturb you. So you're just gonna punch this entire answer in your calculator, this one here. Just gonna punch it out and you should get the height being equals to 0.69 meters, right? Now we're going to do question 6. The statement reads as follows. A group of grade 12 learners stand outside a fire station when a fire engine races past them on a call. The siren of the fire engine emits a sound of frequency 250 Hz while moving at a speed of 20 meters per second past the learners with flashing red lights. The group of learners notice that the sound of the siren changes as the fire engine moves away from them. Take the speed of the sound in air as 340 meters per second. So 6.1, it says that name the phenomenon described in the underlined sentence above. So the underlined sentence says that the group of learners notice that the sound of the siren changes as the fire engine moves away from them. So definitely we're talking of Doppler effect, right? And then 6.2 says that how would each of the following change as the fire engine moves away from the learners? So let's say, for example, these are the learners. This point here are learners, and this is the fire engine moving in that direction. So it's moving away from the learners. So this is the fire engine. So it's moving away from the learner. So now they say, how would each of the following change as the fire engine moves away from the learners? Write only, greater than, less than, or stays the same. So looking at 6.2.1, the frequency observed by the learners. So if something moves away from you, especially in this case, we're looking at the learners and the fire engine. If the fire engine moves away, what happens is, remember, if you know velocity is equals to frequency times lambda, right? So meaning if we want to know about frequency, because the question says frequency, we divide by lambda both sides. So you're going to have frequency is equals to velocity over lambda. So the reason why I'm doing this is I want you to look at the learners. The learners are at this point here, right? So the distance between the learners and the fire engine continues to increase, right? The more the fire engine goes in that direction, the longer the distance, right? The more the fire engine goes in that direction, the longer the distance becomes, right? So the distance is actually lambda, right? It's lambda. So the bigger this lambda becomes, the smaller the frequency, right? So means now that you will hear the sound less and less and less the more the fire engine moves away from the learners. The less you hear the sounds because of waves, sound waves. So the less you hear of the sound. So basically it means now that there's a decrease in frequency, so you can simply write less than, right? So here less than, because it says how would each of the following change the fire engine, or change as the fire engine moves away from the learners. So you can simply write less than, right? So the frequency will decrease as the fire engine moves away from the learners. And then if we look at 6.2.2 says that the speed of sound in air. The speed of sound in air doesn't really change. It stays the same because it really is not affected by the event that is happening, right? So the speed of air is just the speed of air. It's not even the speed of the fire engine. It's just the speed of air. So it's just gonna be the same. So it's just gonna stay the same. Cool. So now we're going to 6.3, right? It says calculate the apparent frequency of sound from the siren observed by the learners. It's really critical that you note this down. It's observed by the learners, right? When the fire engine moves away. So these are critical points. It moves away from the learners at a speed of 20 meters per second. So please check out your formula sheet at the back of your question paper. You'll find formulas of these type of questions under waves, right? We're going to use the formula that looks like this one here. So it's going to be the frequency of the listener being equals to V plus minus V of listener over V plus minus V of S, right, of sound. So multiplied by frequency of sound, right? So we're just gonna, because the it's going to be V, right, velocity of air, which is the 340, and then I'm going to say minus the velocity of the listeners, right, and divide by V plus V of sound, because as the sound moves away, the sound of the fire engine moves away, so it's just going to be positive, and the velocity of listener is this one here, so we're just going to take this sign as negative, right, multiplied by f of s. So it's going to be we're just going to substitute here the v of a is going to be 340 minus the velocity of listener, which it's the learners basically, so the learners are stationary, so it's just going to be 0, divide by 340, and then we say plus the velocity of sound, it's moving away, right? So we're just going to say plus 20 meters per second, and then we multiply by the frequency of sound. So the frequency of sound we're given as 250, right? Just look at the statement above. Let me just show you quickly. The statement above, we were given the frequency of sound. Let me remove this. So this is the frequency we're given as 250. So then now you're gonna find your frequency of the listener, right? If you punch your calculator, you should get 236.11 hertz. So this is the frequency of the listener. I'm gonna do 6.4. Says that draw a diagram to show the advancing wave fronts that are produced by the sound as the fire engine moves away from the learner's. Critical statement. Clearly indicate the learner's position and the direction of the fire engine's velocity in the diagram. So what we know is that we're having the learners here. They are stationary, so these are the learners, right? And then we're having a fire engine here. So this is going to be fire engine. So I'm just going to indicate the direction of this fire engine is moving in that direction. Moving in that direction. So so the diagram of the wave front is like, so you're just going to indicate it basically tells us about the lambda and frequency, right? That the further the fire engine moves, then the larger the the larger the lambda becomes, right? The larger the spaces between these lines. Let me show you. So it's gonna be like this, right? So this means now that the distance between these wavefronts, so it's gonna be larger towards the learners, but it's going to be smaller at the wavefronts, because the wavefront is the one that is emitting sound, right? So meaning that the distance between these wavefronts, which is lambda, is smaller towards the fire engine, but the distance between these wavefronts towards the learners is larger, right? So that's the whole point of this. So you can make it larger here but smaller towards the fire engine, because it's the one that is emitting sound. So your diagram will basically look like this. So that's how you can draw it, right? So this is your diagram. 6.5, there is a noticeable change in frequency of sound, but no noticeable change in the color of flashing red as the engine move past the learners. Explain this observation. So what I need you to note is this. Let's say I draw my lights. This is the light of the fire engine. It almost looks like right, let's just say this is the light. It's on top of the vehicle, right? Yeah, so let's say this is the light. Let me just write lights, and then I'm just gonna write the wave front, so learners and fire engine, and the wavefront that we drew previously looked something like this, right? So what this statement is saying, that there is a noticeable change in the frequency of sound. Yes, there's a change in the frequency of sound. Remember that V is equals to F lambda, right? So frequency is equals to V over lambda. So frequency is affected by lambda, right? So this is the lambda. So there's definitely a change in frequency of sound because of this lambda, right? This lambda becomes larger the further the fire engine moves, right? So there is definitely change, but there's no change in this light here that I just drew here. There's definitely no change. I mean, if you look at if you think of an ambulance, right, or a police car, and you see that light that is flashing, right, it's so fast that you can't necessarily see change. You can't see it lighting and maybe turning off, on, off, right? Something like that. It's really difficult for you to notice that. You only see light that is just flashing, right? So the main reason for that is the following: is because the speed of light is fast that it's difficult for us to notice, and it's given as 3 times 10 to the power 8 meters per second. So that is the speed of light, if you remember clearly. And then the speed of air, so we're given the speed of air, right, to be 340 meters per second. So as you can see here, the reason why you can't notice is purely because of this reason. You can just base it on this reason, right, and say, okay, fine, the speed of light is larger, right? The speed of light is 3 times 10 to the power 8. The speed of air is 340 meters per second. So basically the speed of light is greater than the speed of air. So the fact that it's greater, which means it's easy to notice the speed of air compared to the speed of light, right? It's easy to notice speed of air compared to speed of light. So that is the reason for this question here. Do question 7, and the statement reads as follows. A metal sphere X with a charge of 5 nanocoulombs is suspended by an inelastic thread of a negligible mass which is tied to the ceiling at point M. Another sphere Y on an insulated stand has a charge of minus 8 nanocoulomb and is brought closer to sphere X until their centers is 20 millimeters. So the diagram, as you can see here, explains what is written in the statement. So we have sphere X and sphere Y, and this is the thread that ties the sphere X to the ceiling. So this would be a ceiling, right? And this is the distance between both spheres. And going to 7.1 states that we should state Coulomb's law in words. Coulomb's law. So Coulomb's law states that the magnitude of the electrostatic force exerted by charge 1 on charge 2 is directly proportional to the product of the charge. The product of charge 1 and 2 and inversely proportional to the distance, the square distance between them. Right, so now we're gonna do 7.2, which states that calculate the magnitude of the electrostatic force that sphere Y exerts on sphere 2. So we're just going to calculate the electrostatic force that exists between these two charges, charge of sphere Y and sphere 2. So for us to calculate that electrostatic force, we're going to say use the equation of F is equals to K Q1 and Q2 divided by R squared, right? And we know that K is equals to 9 times 10 to the power of 9, and then charge 1 is going to be equals to 8 times 10 to the power of minus 9, and charge 2 is 5 times 10 to the power of minus 9. Divide by the distance between them, which is 20 millimeters, and we're going to change it into meters, so we're going to multiply it by 10 to the power of minus 3 all squared. So if you notice, I didn't include the sign of the other charge. As you can see here, the charge of Y is minus 8 nanocoulombs, but you can include it because force has direction, right? You can just include it if you want, and you punch the calculator, you should get 9 times 10 to the power of minus 9 newtons. So you can, if you include that negative, it's just going to be negative 9 times 10 to the power of minus 9. So this this sign will just indicate the direction of the force. If you choose right to be positive, then left would be negative. So now we're going to do 7.3, which says that we must draw the resultant electric field pattern produced by sphere X and Y. Right? So we know that the sphere X is positive, right? It's positive 5 nanocoulombs, and the sphere Y, it's negative 8 nanocoulombs, and the movement of charges is from positive to negative, right? Now, for us to draw the electric fields, we need to indicate our sphere. So we have sphere X, which is positive, and we have sphere Y, which is negative, right? And I said that charges move from positive to negative, right? So we can simply indicate that this one here, the direction of charge, and we'll put another electric field and the direction of charge. So you can simply draw this, which is not really difficult, and another electric field, direction of charge, and then you indicate the rest like this and like that. So this is going to be your electric field, showing the charges that are moving from sphere X to sphere Y. Now 7.4 states that sphere Y is now moved closer and makes contact with sphere X, after which sphere X is repelled. So calculate the new charge on sphere X. So what's happening here is this sphere Y is brought closer to sphere X, and when they combine together, they now have the same charges, right? We all know that different charges attract and like charges repel, right? So the movement of these charges will go in that direction and that direction, but these ones will come closer, right? So that's what happened here. So when they combine, when sphere X combines with sphere Y, they will have the same charge and repel after that. So let's do the calculation of this one. So we're gonna have our Q of X new, because we want to know the charge of Qx, the new charge. Obviously both will have the same charge, so it's going to be Q1 plus Q2 divided by 2, right? You all know this formula. And the charge of sphere X is 5 times 10 to the power of minus 9, and then we will say plus the charge of sphere Y, which is minus 8 times 10 to the power of minus 9, and then we divide by 2, and the answer that you need to get is minus 1.5 times 10 to the power of minus 9 coulombs, right? So this is the charge that is on each sphere. So basically sphere X will have this charge of minus 1.5 times 10 to the power of minus 9 coulombs, and sphere Y will have this same charge of minus 1.5 times 10 to the power of minus 9 coulombs, right? But we are mostly interested in the charge of sphere X. Okay, so now we're going to do question 8. We are given the statement here, which reads as follows: a battery with an EMF of 8 volts and an internal resistance R is connected in the circuit below. So if you can see, clearly see the circuit, we have our internal resistance here, we have the voltage here, we have our battery here, and we have our open switch S1, and then we have our resistors R1 and 2 ohm resistor. We have this another switch here S2, and we have our ammeter here and another resistor there. So yeah, that is our circuit. And the statement says that if switch 1 is closed, the reading of the ammeter, or of the voltmeter rather, is going to be 6.86 V, and on the ammeter is going to be 2 amperes, right? And then 8.1 says that explain the meaning of an EMF of 8 volts. So this 8 volts just means the total energy supply by the battery, right? We were told about this 8 meter volts, right? 8 volts of the EMF, right? So it's just the total energy supply of the battery. Eight point two, we are asked to calculate the internal resistance of the battery, right? So the battery has an internal resistance, as you can see there. It's the small r. So we're just going to calculate that internal resistance. So for us to calculate the internal resistance, we know that the equation for EMF is EMF is equals to, is equals to I multiplied by the small r plus I multiplied by the large R, right? So remember that we were told that S1 is closed, meaning the switch, this switch here that is open, is closed. So we're just gonna need the current, which we're given to be 2 amperes, right? And we know that E is equals to 8 volts, right? And this big R here is the total resistance, right? So what you're just gonna convert it into V over I, right? We already know this voltage, which is the given one here, which is 6.86, and we're just gonna substitute the I here. So and then we find this small r. So let me do it right next here. So we have EMF is equals to I multiplied by the internal resistance plus I, which is the current, multiplied by the total total resistance, right? E is equals to I multiplied by R plus, so we're just gonna change the R. We know V is equals to IR, right? So divide by I, so R is equals to V over I, right? So we multiply by V over I, right? So this I will cancel out with this I, so it's E is equals to IR plus V, right? And we need this small r here, so we're just gonna transpose this V to the other side, so we will have E minus V is equals to IR, then divide by the I, both sides. We will have the small r, which is the internal resistance, equals to E minus V over I, right? So the EMF we were given to be 8 minus the voltage, which was 6.86, divided by the current, which is 2, right? And you should get an answer of 0.57 ohm. So this is the internal resistance of the battery. So now 8.3 says that we must calculate the value of the unknown resistor R, right? So if you look at the circuit, we have this unknown resistor R and all the resistors we have, and now we just calculated the internal resistance, so we just need this R. So what we need to do here to calculate this, we need to identify our EMF being equals to I small r plus I large R. So this R is the total resistance, right? And we already know the current already know the current, we already know R, we already know this. So we're just going to equate into the total resistance, right? So we can simply say, let me just do it on another page. In the question as read, we want to identify R1, right, which is parallel to the 2 ohm resistor, right? Please note this, they are parallel to each other. So now, for us to find this R1, we will say the EMF. So we're just going to use the equation of the EMF. We first want to find the total resistance of the circuit. EMF is equal to IR plus IR total, right? And we know the EMF is 8, being equals to the current, which is 2, and the internal resistance we found to be 0.57 in the previous question, plus 2, which is the current, and then R total, right? And then we transpose this to the other side. We have 8 minus into 2 times 0.557, sorry. So it's 0.57 and is equals to 2 R total, right? So then we're going to divide by these 2 here, divide by these 2. We will have R total is equals to 8 minus 2 multiplied by 0.57 divided by 2. So your R total is supposed to be equals to 3.43 ohms, right? So now that you have your total resistance of your circuit and we want to find R1, so the total resistance is the combination of the parallel resistance plus the resistance in series, right? And what you need to note is that the R total we just found, so the main aim is to find the R parallel, right? Because the R parallel is a combination of R1 and the 2 ohm resistor, right? So let's first find the R parallel using this equation here. So we already know R total and R series. The R series is the 2 ohm resistor of the circuit. So the R parallel is 3.43 is equals to R total, sorry, is 3.43 equals to R parallel plus R series, which is 2. Transpose the 2 to the other side, so you have your R parallel being equals to 3.43 minus 2, which is equals to 1.43 ohms. So this is your resistance in parallel, right? Now it will be simpler for us to find the resistor R1, right? So to write down your equation for the parallel resistance, you're going to say 1 over R parallel is equals to 1 over R1 plus 1 over 2, which is the 2 ohm resistor, right? So for us to find this R1 here, we already know this R parallel, right? Let me just write the answer. So it's going to be 1 over 1.43, right? Equals to 1 over R1 plus 1 over 2 ohms, right? So you're just going to find the common denominator on your right hand side here. So it's going to be 2R1, right? And R1 goes how many times into R1? It goes once, and then 2 remains. And then plus 2 goes how many times into 2 once, and then R1 remains. So you're going to have 1 over 1.43 being equals to 2 plus R1 over 2R1, right? So the main aim here is to equate into R1. So you're going to cross multiply here, and you have 2R1 over 1.43 being equals to 2 plus R1, right? And then you cross multiply here, let me put the brackets. Then you have 2R1 equals to 1.43 into 2 plus R1, right? And then this 1.43 will multiply everything that it finds inside the brackets. So you're going to have 2R1 equals to 1.43 times 2 plus 1.43 R1, right? So you're going to collect the like terms. So this 1.43 will go to the other side here. So it's going to be 2R1 minus 1.43 R1, 1 equals to 1.43. So this is 1.43 times 2, right? And then you can just factorize, or you can just subtract both, or just factorize R1. It's going to be R1 being equal to 2 minus 1.43 equals to 1.43 times 2. Then you divide with this expression here. You will have your R1 is equals to 1.43 times 2 divided by 2 minus 1.43. And then from here you can just simply punch in your calculator the entire expression here. You should get your R1 being equals to 5.02 ohms. 8.4, we are asked to define the term power. So power, it is the rate at which work is done, right? So there's many definitions, but this is one of them. Now 8.5 says that switch S is now open. Question says that 8.5.1, what effect will the power dissipated by R1 have? Write down only increase, decrease, or remain the same. So 0.5.1, we're just going to say increase, right? 0.5.2, we are asked to explain our answer. Why are we saying the power dissipated by R1 is going to increase? So if you remove the resistance, which was 2 ohms, right, because of that open switch, that means now the resistance of the circuit will increase. So the resistance of the circuit will increase, right? And an increase in that resistance will mean now that the potential difference of the circuit will also increase, right? So an increase in these two results in an increase in power, right? Why am I saying that? So power will increase. An increase in potential difference and resistance results in power increasing. That is because power is equals to IV, right, which is equals to I multiplied by IR, right, which is equals to I squared R. So an increase in resistance results in an increase in power, right? An increase in voltage will definitely cause an increase in power. So hence I said increase in resistance, increase in potential difference results in an increase in power. So now we're going to do question 9. We are told that the diagram below shows a simple generator, right? If we just analyze this generator, we can see that this is a magnet, right? And this is another magnet, right? And this part A, you can see this is a coil. So this coil is rotated. Looking at this arrow is rotated clockwise. So as it's rotated and these magnets are brought closer, current is induced, right? So when current is induced, it's going to flow into this circuit here. As you can see, this is a circuit, right? So yeah, and we are shown part B, which just basically tells you that these are split rings, right? They are split, as you can see here. It's an open space. So these are split rings, and this is a coil. Fine. So we've analyzed this magnet. So what's important is for you to go and look at your DC generator and your AC generator. Look at the diagrams and be able to identify how does DC generator look like and how does an AC generator look like. Fine. Let's go to the question. So 9.1 says that we must identify whether this is an AC or a DC generator. So basically this is just going to be a DC generator, right? So as I said, you need to be able to identify how you see a DC generator and how you see an AC generator. Then 9.2 says that we must give a reason for our answer. Basically, as I wrote here, I said split rings, so you can simply write split rings. So you see it by split rings, right? That's one of the reasons. There's more reasons to that, right? So 9.3, which says that write down the name of part A. We already wrote it. It's a coil, right? So this is part A. As I said, I explained that this coil is rotating, right? So hence I said it's part A. So, coil. So 9.4, we are told to describe the energy conversion that takes place in the generator. So right, this is basically mechanical energy that is happening here, right? Because you're rotating this coil, and at the same time, these magnets are coming closer and going away, coming closer, and current is induced when that happens, right? As it's induced, it flows to this circuit here, as you can see. So that is the mechanical energy. So this mechanical energy is converted into electrical energy, because the mechanics happen here, and then it's converted into electrical energy, because that's when now this current flows because of whatever that is happening in this section here. So you can simply write down, or is it? You can simply write down mechanical energy to electrical energy. Fine. So now 9.5. Let me erase this. 9.5, it says that the maximum EMF generated is 15 volts, right? Draw a sketch graph of EMF versus time for 1.5 circles. So it's important for you to note this. 1.5 circle for this generator. So if we were to draw, let me draw it in a clean, draw our EMF versus time graph. It's going to look something like this. Okay, let me just draw it nicely. So it's going to look like that. And then because it's a half circle, so it's just going to be like that. So it's going to be like that, right? So these circles are equal. So let me just indicate properly. Erase this part. So it's going to look something like that. Right, and the maximum, which is this part here, is going to be the 15 volts. So this would be time at the bottom in seconds, and then this would be EMF in voltage. So this is our EMF versus time graph. Now 9.6, it says that the specifications of a professional hair dryer are as follows. So this is the hair dryer, and it has 2100 watts, and it is an AC motor of 240 voltage, right? So 9.6.1, we are asked to define the RMS for an alternating voltage, right? So the DC potential difference, which dissipates same amount of energy as AC. So it's a DC potential difference which dissipates same amount of energy as AC. So that is the definition of RMS for an alternative voltage. Right, so let me remove this. And now 9.6.2 says that what is the RMS voltage for the hair dryer? So we are given, right, this is the RMS of the voltage. So it's 240 volts. and 9.6.3, we are asked to calculate the maximum current that might flow through the hair dryer. So we want Imax, right? Maximum current, right? So for us to find maximum current, we can use the equation for power, right? So the average power is equals to IV, right? And we are given the power to be, let me look, we're given the power to be 2100, so it's 2100 watts, and AC is 240, right? So it's 2100 watts equals to AC is 240, we're given as 240, so it's going to be I into 240. So the I that we will calculate here is the RMS I. We'll divide by 240 both sides, divide by 240 both sides. So I RMS is going to give you 8.75 amperes. But we want the Imax, maximum current, right? So it's going to, so this you'll find at the back of your question paper, the equation for Imax, right? So it looks like this. So now we're just going to write this root of 2 multiplied by your IRMS, which is 8.75, and then your Imax is equals to 12.37 amperes. So this is the maximum current that is circulating. To question 10, the statement reads as follows: the apparatus shown below allows for several variables in the investigation of photoelectric effect. A learner sets up the apparatus and measures the maximum kinetic energy of photoelectrons emitted from the surface of metal X using different frequencies of incident radiation, right? As they said, they use different frequencies of incident radiation. Fine, so this is a diagram. This is the apparatus that is set by the learner. We have our metal X here. We have an incident radiation. They're using different frequencies to emit light into this metal X, right? And then this is the collector. We're having our glass tube here, and basically they're saying that this is vacuum, right? The entire space here is a vacuum, and then we have our ammeter there, we have our open switch there, right? So then these are different metals that are used. So we have our sodium, our magnesium, our aluminium, and zinc. So they have their energies here, different energies, right? But we used metal X, so we don't know which metal was used here. We'll probably know later on in the question. So now 10.1 says that we must describe the photoelectric effect, right? So if I were to describe it, it is basically the process whereby electrons are ejected, right? Ejected. Okay, let me write this term nicely. So it's a process where electrons are ejected from a metal surface when light of suitable frequency is incident on the surface. So that is photoelectric effect, right? 10.2 says that light with different wavelengths is shown onto metal X and the kinetic energy is measured. So light of different wavelengths, different frequencies, you can say, is shown on metal X, right? And we measure the kinetic energy of each, right? Fine. So 10.2.1 says that name the independent, dependent, and controlled variables of the experiment. So as you are using different frequencies, right, of light, basically it tells you that the independent variable will be the incident of light, because using different frequencies, incident of light, using different frequencies of light, so you are the one making the choice of using different frequencies, so it's independent. And the dependent variable will be the kinetic energy, right? Kinetic energy depends on what frequency of light you are using. So kinetic energy is going to be the dependent variables, kinetic energy of those electrons, right? And our controlled variables will be the type of metal that we use. We can use the aluminium metal and we stick by it, or we can use just any type of metal and we'll stick by it. So that is controlled. Okay, so now we're going to do 10.2.2, right? It says that when ultraviolet light with a wavelength of 280 is shown onto metal X, the kinetic energy of the released electron is 5.74 times 10 to the power of minus 20 joules, right? Identify metal X in the table given. So what you need to do is we need to identify the work energy, right? And it will tell us which metal was used in this scenario here in 10.2.2. So for us to do that, we are going to write down the information given. So we are given lambda of 280 nanometer, right? Lambda, which is wavelength, and we're given the kinetic energy be equals to 5.74 times 10 to the power of minus 20 joules, right? And we want to identify the work done, right? So for us to do that, we'll use the equation of energy being equals to H, right? Which is the Planck's constant, and multiplied by C over lambda, which this is also equals to the work plus kinetic energy. So this formula, you can find it at the back of your script in the formula sheet, right? Then you can simply say, okay, fine, you're having H times C over lambda is equals to work plus kinetic energy. So already know kinetic energy, already know Planck's constant, we know the speed of light, we know the wavelength, we can simply find this, right? So the Planck's constant is 6.63 times 10 to the power of minus 34, multiplied by the speed of light, which is 3 times 10 to the power of 8, and then we divide by the wavelength, which is 280. Because it's nano, so it's 10 to the power of minus 9 meters, equals to work plus our kinetic energy, which is 5.74 times 10 to the power of minus 20, right? So we're going to transpose this kinetic energy to the other side to find our work done. So work is equals to 6.63 times 10 to the power of minus 34 times 3 to the power times 10 to the power of 8, divide by 280 times 10 to the power of minus 9 minus 5.74 times 10 to the power of minus 20, right? So you're just going to punch in your calculator this entire expression here, and your work is supposed to be 6.53 times 10 to the power of minus 19 joules. So this is going to be your work done, right? So we need to identify which metal is this, right? Using this work done of 6.53 times 10 to the power of minus 19. So we're going to go back to our diagram and our table rather. We got 6.53. So 6.53 is this one here, right? So now we know that the metal that was used, it's actually aluminium. So we can go back and indicate which metal is metal X, right? So simply say metal X is aluminium. Cool. 10.2.3 says that the maximum kinetic energy of electrons ejected by the ultraviolet light is greater than the maximum kinetic energy of electrons ejected by the blue light. So we're comparing an ultraviolet and blue light, right? Explain why this is so. Why the ultraviolet light is the kinetic energy is greater than that of the blue light, right? Why is that so? So you can simply look at the, if you're looking at the ultraviolet light, we can look at the what is this, the lambda, which is the wavelength. The wavelength, you can just go to your electromagnetic spectrum if you have it. Obviously this would be an exam, so you won't have access to that, but if you know your electromagnetic spectrum, you'll know the wavelength of your ultraviolet light, right, which is 1 times 10 to the power of minus 8 meters, right? And the wavelength of your blue light is equals to 5 times 10 to the power of minus 7 meters. So you can easily compare these two. I mean, like, which one is bigger and which one is smaller, right? It's clear that the wavelength of this wavelength, right, is, because it's 10 to the power of minus 7, it is larger compared to this one of 10 to the power of minus 8, right? Because yes, 5, but 10 to the power of minus 7, so it's smaller, so it's larger, sorry. So now when you want to identify kinetic energy, remember that our formula to identify energy is equals to work plus kinetic energy, and we are told that the kinetic energy of the ultraviolet is greater than the kinetic energy of blue light, right? So which basically will be determined by your wavelength, because E is equals to H multiplied by C over wavelength, right? So if this wavelength is smaller, it will eject a larger energy, right? So larger energy will mean larger kinetic energy, right? Hence the wavelength of the ultraviolet is smaller, right? So the smaller the wavelength, the larger the energy, meaning the larger the kinetic energy. But the larger the wavelength, it will give you the smaller energy, right? Photon of light, it will give you smaller energy, and then this smaller energy will result in smaller kinetic energy, right? So that's how you can compare these two, right? Let me just write it properly here, just for us to see. So we're having E is equals to H multiplied by C over this equals to work plus kinetic energy, right? And I said the ultraviolet light has a lambda which is equals to 1 times 10 to the power of minus 8 meters, right? So if you were to indicate that in this equation, you say E is equals to H multiplied by C over 1 times 10 to the power of minus 8 is equals to work plus kinetic energy, right? And if you were to write the kinetic energy of this, you're going to say H multiplied by C over 1 times 10 to the power of minus 8 minus work done is equals to kinetic energy, right? So this 1 times 10 to the power of minus 8 is smaller compared to that of the blue light, right? Because if you, so this E is for the ultraviolet, so let me just write ultraviolet light, right? So let me write that of the blue light. E is equals to H multiplied by C divided by the wavelength of blue light is 5 times 10 to the power of minus 7 minus work equals to kinetic energy of the blue light, right? So I want you to note this the wavelength of the ultraviolet is 1 times 10 to the power of minus 8, which is smaller compared to this 5 times 10 to the power of minus 7. So if this is large, right, it will produce small energy. So this is going to be small. So if this energy is small, therefore the kinetic energy will be small, right? And then looking at this one, it has a smaller wavelength, will produce larger energy. So large energy will result in large kinetic energy. So that's how you can compare it. You can compare it using this form here. If you understand the wavelength of these two properties, one property of light and the ultraviolet of light, then you'll be able to answer the question. Or you can use you can check your memo. If you rely on memos, you'll use that definition. But this is one way which I appreciate in explaining this problem here. So